As organizations prioritize data sovereignty, engineers face a difficult mandate: bringing hyperscale, data center-level artificial intelligence operations directly into standard office environments. Multi-agent orchestration frameworks require models capable of deep chain-of-thought reasoning. To maintain strict logical fidelity during complex workflows, these models must be deployed in an uncompressed 16-bit floating-point format. Low-bit quantization workarounds introduce degradation that high-stakes agentic frameworks cannot tolerate. Currently, the frontier of open-weight reasoning is dominated by the DeepSeek V3 and R1 architectures. These models are massive, built upon a 671 billion parameter count. Through a mixture of experts architecture, out of 671 billion parameters, a sparse subset of only 37 billion activates per token. However, the model's router mechanism requires instantaneous access to the entire 671 billion weight matrix. Every single weight must reside simultaneously in active memory. Storing 671 billion parameters in uncompressed 16-bit precision requires between 1.34 and 1.54 terabytes of highly accessible video RAM. You must also provision additional overhead capacity to hold the massive key-value caches generated by multiple agents communicating back and forth. For an infrastructure engineer evaluating hardware, raw computational speed is secondary. The mathematical prerequisite is securing a system capable of pooling over 1.3 terabytes of active memory. Localized desktop AI development has historically been built entirely around the NVIDIA ecosystem, utilizing the massive processing throughput of discrete graphics cards. This chart compares the total pooled video RAM of desktop hardware configurations. A workstation running 4 NVIDIA RTX 6000 ADA cards physically limits out at 192 gigabytes. Similarly, 2 clustered DGX Spark units provide a maximum of 256 gigabytes. When plotted against the 1.3 terabyte baseline required for the uncompressed DeepSeek model, both NVIDIA enterprise desktops represent an immediate mathematical failure. They cannot physically load the weights. Apple's unified memory architecture presents a distinct alternative. A 4-node Mac Studio M3 Ultra cluster successfully pools 2,048 gigabytes of VRAM, comfortably crossing the model's footprint with hundreds of gigabytes remaining for cache overhead. Because traditional enterprise NVIDIA desktops fall short of the memory capacity prerequisites for this tier of inference, IT directors look toward interconnected Apple silicon. Capacity is only the initial requirement. Autoregressive decoding relies entirely on memory bandwidth, as the system must physically fetch 37 billion active parameters across the bus for every single generated token. A single DGX Spark operates on a 273 gigabyte per second memory bus. A single Mac Studio M3 Ultra delivers exactly 3 times that speed, achieving 819 gigabytes per second of memory bandwidth. To reach 2 terabytes of total capacity, you must physically distribute the workload across 4 distinct Mac Studio chassis. This introduces a heavy reliance on network synchronization to execute tensor parallelism. Traditionally, distributed inference across Macs relied on standard transmission control protocol over Internet Protocol via Thunderbolt. This routing requires data to drop from application memory down into the kernel, get processed by the CPU, wrapped in headers, and sent across the cable. Each step adds compounding latency. The synchronization penalty hits roughly 300 microseconds per iteration, which completely strangles overall token generation speeds. Under standard networking protocols, pooling 4 high-bandwidth Macs results in a disjointed, severely throttled hardware array rather than a cohesive tensor parallel supercomputer. In December 2025, Apple altered this computational landscape with the release of macOS Tahoe 26.2. This update introduced native, kernel-level support for remote direct memory access over Thunderbolt 5. Remote direct memory access allows one machine's GPU to directly read and write to the memory space of an adjacent machine's hardware. It entirely bypasses both operating systems, avoids buffer copies, and eliminates CPU interrupts. By operating at the absolute limits of the Thunderbolt 5 controller, RDMA reduces internode interconnect latency from 300 microseconds down to between 5 and 9 microseconds over an 80 gigabits per second physical link. This chart measures token generation scaling. The gray bars illustrate the performance decay of standard TCP over IP. As nodes are added, overhead causes throughput to drop. But activating RDMA, shown in blue, achieves near-linear scaling, reaching a sustained 32.5 tokens per second. RDMA over Thunderbolt 5 provides the high-bandwidth, low-latency fabric that allows 4 distinct consumer units to replicate the synchronization speeds found in hyperscale data centers. Because there are currently no network switches capable of routing RDMA over Thunderbolt 5, deploying this cluster requires strict, zero-hop, point-to-point physical connections. Engineers must configure a precise full-mesh topology to prevent internal PCIe bus collisions. This requires exactly 6 physical cables mapped across the EN2, EN3, and EN4 ports, directly linking every node to every other node in the cluster. Once physically cabled, orchestration frameworks like EXO and MLX Distributed evaluate the resources and mathematically shard the 1.3 terabyte model evenly across the physical mesh. Apple Silicon does have a distinct weakness. An M3 Ultra outputs roughly 43 teraflops of 16-bit compute, compared to the 210 teraflops of an NVIDIA RTX Ada. This creates notably slower prefill speeds when processing massive context windows. Multi-agent frameworks mitigate this through prompt caching. By storing processed context in the cluster's massive 700 gigabyte memory overhead, agents skip the slow prefill stage on all subsequent interactions. By combining a meticulously cabled full mesh network with software-level prompt caching, infrastructure engineers insulate the max processing weaknesses while exploiting its vast memory capacity. When enterprise NVIDIA desktop configurations lack the physical capacity to load a model, an organization must abandon the desktop form factor entirely and scale into data center architecture. Housing 1.3 terabytes of uncompressed weights within the NVIDIA ecosystem requires procuring dedicated enterprise hardware, typically an 8-node H100 or GH200 server configuration. This visual breaks down the economics of scale, starting with capital expenditure. Acquiring an 8-node enterprise server rack demands a massive capital layout, approaching $750,000. The localized Mac Studio cluster, fully cabled, totals under $50,000. Achieving trillion-parameter inference capability is no longer strictly gated by multi-million-dollar hardware procurement cycles. The financial barrier to entry has lowered considerably for mid-tier organizations. Evaluating localized infrastructure requires calculating long-term operational expenditure, dictated by continuous power draw and thermal output. On the right, the NVIDIA H100 array draws between 5,600 and 10,000 watts, necessitating dedicated 240-volt circuits and aggressive HVAC cooling. In contrast, the highly efficient 4-node Mac cluster draws under 600 watts, plugging safely into a standard 120-volt office outlet. It generates minimal ambient heat and requires absolutely zero specialized cooling infrastructure. This crucial networking update enables a cluster of desktop Macs to replicate the performance of specialized enterprise fabrics. It provides organizations with the reasoning fidelity of a trillion-parameter model while maintaining total data sovereignty on an engineer's desk.